I will tell you what, though. You know who's happy to have a snow day is a little boy on his birthday. My son turned 7 yesterday, and he got a bonus home day to play his beloved video games, not having to go to school, and to play with his older sister who flew in to surprise him. She's 15, and he idolizes her, so that was fun. They got to spend extra time together, courtesy of Mother Nature. And I'm told there's more snow on Thursday, maybe? I don't know. If it looks like there's going to be anything that is accumulative, I will probably pull the plug and work from home that day. Because last time that happened, I spent an hour like white-knuckling the drive home. I drive a 2008 Corolla. It is the opposite of good on snow. So, yeah, it only has 76,000 miles. I know it's old, but it still works. So, anywho. We have, let's see, let's get the screen share going so we're all looking at the same thing. I have formative assessment number 3 up. Had a chance to look over everyone's answers this morning. Looks like there were mostly good parts, a few areas of confusion with respect to power that we can talk about. And your scores should be updated as well. So first question, this went exceptionally well. What type of decision would go with a type 1 error? Who wants to tell me what you wrote down? Zoomers or roomers? I'm watching the chat window. I'm listening with my ears. What's a type 1 error? Reject a hypothesis? When what is true? Yeah, we got answers coming in the chat window. False positive, false alarm. Type 1 is when you say there's significance when there is not. Yes, so when you reject the null but you shouldn't have. A few of you gave me an example of a positive COVID test, but you don't really have COVID. That is a false alarm. I'm not sure that's possible, actually. If you have enough whatever to detect the test, I don't know that that's a possible result, but in theory it is. There's false positives in all walks of life. And type 1 error is something that you, in theory, have control over. What do you do if you want to have less of a chance of a false positive? Reduce the alpha. Yeah, your alpha level. Your decision as to where unexpected starts. 5% of the time or less, for instance, is an alpha of 0.05. If you want to have less of a chance of a false positive, you make it harder to say that you found something. Then it's harder to make that kind of error. However, then you set yourself up for being more likely to make a different kind of error instead. So what kind of decision would result in a type 2 error? What's type 2? If type 1 is a false positive, what's type 2? False negative, yeah. When there was something to be found, but you missed it. So a miss or a false negative. Or a COVID test that says you're fine, but you're actually sick. That would be bad. And type 2 error is related to power. That's the next question. 1 minus type 2 error is power. So if a type 2 error is missing something that's there, then the opposite of that is finding something that's there. So power is your probability of detecting an effect that's really there. If you don't detect an effect that's really there, that's a type 2 error instead. A miss or a false negative, type 2 error. Yes, indeed. And type 2 error is conventionally supposed to be what in the social sciences? Is it also 0.05? You would think, but no. It's 0.2. Yeah, it's in the where I got that is because we are told to strive for 80% power, which translates into a 20% type 2 error rate. So for whatever reason, conventionally type 2 errors are less of a problem than type 1 errors. We're more willing to accept them. As a scientist, though, you can decide which is more important to you and change the study accordingly. So, any questions on number 1? Okay, so then power. So statistical power, conceptually, is the probability of finding an effect that's there. That's how I would define it. And we are told to increase our power as much as possible. We want to run high-powered studies. So what are the things that we can do that would translate into higher power? There's 3 things I can think of, and a few of you mentioned a 4th that's sort of in there, but it's a little bit different.
A large sample size?
Smaller sample size or lower sample size for more power?
Larger sample size.
More sample size, yeah. More people, more power. That's really the only thing that you can control without having a negative consequence. The more people you have, the more likely you are to find an effect that's there. So let me pull up a slide from lecture 2 that had this concept. So this is slide 56. I simulated a correlation of 0.3 in 100,000 fake people, drew 1,000 samples each of 42 people, 63 people, or 85 people, and this top plot right here is the distribution of what R was across those 1,000 replications at each sample size. And so when you have fewer people, there's more noise in what the effect turns out to be. The effect is less consistent across repeated samples when you have fewer people than when you have more people. So the corresponding t-test statistic that goes with these correlations is shown in the bottom plot here. And I have a dividing line by the red dashed lines as to where significance starts at a t of roughly 2-ish. So the replications that fall to the right means that we would reject the null hypothesis and say, yes, this correlation is significant. The proportion of times that happens is power. The proportion of times to the left where we say, nope, sorry, didn't make the cutoff for significance, that's type 2 error. So all things being equal with respect to effect size, which is what this correlation is, more people, more power. So more people, more power, more effect, more power. So if this correlation was 0.5 instead, more of the replications, regardless of sample size, would be significant, meaning that the correlation is different than 0. But you can't control your effect size. You're stuck with whatever you're trying to find. You can try to do things to minimize noise. So you can try to eliminate confounds by design. You can try to add covariates that would soak up extraneous reasons why people are different from each other. You can do things like that to try and increase your effect size, but effect size is the thing you're kind of stuck with. So more power comes from more people, more effect size, and what's one more thing you could do, but it's probably not advised? Significance level, yeah, alpha. If you make it easier to say that something is significantly different than 0, you make it easier to find it, which means you increase your power. But you do so at a risk of having more false positives. So in theory, you can increase your alpha to increase your power, but that may be questionable because then you're changing your decision criteria the other way in a problematic way. And a few of you mentioned type 1-tailed tests. You can think of that as analogous to changing your alpha. If you change from a 2-tailed test to a 1-tailed test, it's like you've doubled your alpha because you put all of your area on one side instead of 2 sides. Question, if the power table came out to say 200, would it be beneficial to have n of 300 to argue that is how you increase your power, or is that redundant? Is doing too much not relevant for a significant outcome? Good question. So the question is about the use of these sorts of heuristics. This is a power table for a correlation at an alpha of 2-tailed 0.05. So for instance, the question was, if I had, say, 80% power is this blue line right here, so 194 people. So if I want to detect a correlation of 0.2 or greater, I need at least 200 people to do so. And the question was, what if you have 300? Then you have more of a chance of detecting it. So then you would have roughly 92% chance, 93% chance, somewhere between these two cells with respect to power. So the extra 100 people going from 200 to 300 is not as important as the going from 100 to 200. There's diminishing returns with respect to sample size. And you can see that in the table here. Like to get to increasingly higher power, it's exponentially higher relative to what it takes to move in this part of the table. And power is related to replicability. So if I have a correlation of, let's say, 0.4 is what is true in the population, and I only have 12 people, and I found this to be significant, well, the power was only 0.25, meaning only 25% of the time would I have gotten lucky like that. So it's unlikely with a sample size of 12 that you would find a correlation of 0.4 to be significant. 75% of the time you would not, as a prediction. So that's why power is important for replicability. All right. Other questions on power or things to increase power?
So to count it significant, the power has to be 95 and up in social sciences.
We are told to aim for 80% as a conventional level of power. But the higher it is, the more of the replications you would expect to be significantly different than 0 at that effect size.
I was just trying to understand power from the alpha level perspective.
Oh, if you had a different alpha, let me find, here we go. This is two-tailed alpha 0.05. You would have to have a completely different table at a different alpha level. So what that would translate to would be at an alpha of 0.01, for instance, this little red line, I think it would be moved over to the right. Like where unexpected starts would be further out. So there'd be fewer trials that would fall into unexpected territory with respect to being different than the null. But that's a good point. All of these computations are based on the idea that you know what is true in reality. So power is always tied to a specific effect size. And this is why it becomes tricky when you get to the point where people come to you for help and they say, I need a power analysis for my dissertation proposal, or I need a power analysis for my grant proposal. And my first question is, power for what? Like, what specifically are you trying to power? Which effect in your model, and by what metric are you gauging it? You got to answer those questions before you can compute power.
Can you give a real-world example of how someone would respond to that?
Yeah. I can give an example from a slide.
Yeah.
Would that work?
Yeah.
Okay. Let me skip ahead to answer that question. I'm in lecture 3, slide 22. So this is the example of predicting annual income from low, middle, versus upper class as a 3-category predictor. And here are 4 different power calculations that are possible out of just this one analysis. So power for what? Well, do I want to have sufficient power to detect the difference in income between people who rate themselves as lower class versus middle class? Well, to answer that question, I need to know what is the effect size. So we got to work backwards to get to that, because that's step 4, right, in our 4-step process of answering research questions. Step 1, code the variables. Step 2, put them in a model. Step 3, find out what else you want to know the model doesn't tell you and ask for it. Step 4, compute effect size. So here's what I found. Here's my slope in this case. You zoom in so we can see the numbers a little better. The slope is 8.85. Standard error is 1. So that gives me a t-value of estimate over standard error of 8.82, meaning that slope is 8.8 standard errors away from the null of 0. If I back translate that t-test statistic into an r, so here's the conversion formula. It's t over t squared plus denominator degrees of freedom. My r is 0.3. So if this was a study that I was reading in the literature and I had this information, I could say, well, based on previous research, I expect an effect size for this particular slope of 0.3. I could also convert the same t-test statistic into a d effect size, which is a standardized mean difference, which is yet another table with respect to the predicted power by sample size. But that translates into a per group n of more than 45. So that, let me see if I can get both things on the same slide at the same time. I don't think I can. R of 0.3, I need at least 45 people per group to get to an R of 0.3. So based on that, I only need 45 people per group. That's not bad. Well, what if I want to have sufficient power to detect lower class versus upper class? Well, from this study, there are very few people who put themselves into the upper group, so that slope has a lot more noise to it. That translates into a t that's only 3 standard errors away from the null hypothesis, or an R that's only 0.13. So that's a much smaller effect size, and now I need 175 people per group to pull that off. What about the third comparison that's not given directly by the model, but that is implied, the difference between the non-reference groups of middle versus upper? Well, this one is the worst yet. The slope was 2.13, but the standard error was 3. Like, this is well within expected territory. That's nowhere near significant. If the true slope were 0, I'd find a slope of 2 like 48% of the time. That translates into an R of 0.03. And now I need 2,100 people in each group to have 80% power to find that. And if the poor researcher or grad student or postdoc was like, can I just power the model? Can I do that? Sure you can. My model had an R square of 0.10. My model captured 10% of all the variance in income by these 3 groups. Well, that, if I square root that R, that translates into an R of 0.32. And now I'm back to power of 85. So this is what's running through my head when someone says, I need a power analysis. Power for what? Like, this is one variable of one outcome, and I've got 4 very different answers as to what the sample size would be. In reality, the conversation usually goes like this. I can afford 150 people. What can that buy me? Okay, then we work backwards. And so then what I do is simulate data with 150 people until I get an 80% empirical power rate, and I figure out what effect size that corresponds to. And then I say, you can purchase an effect size of this or greater with 150 people. And yeah, this type of demonstration that made these pictures here, simulating something where you know the truth and seeing how often the truth comes back as significant, this is exactly what I do in power analyses. You make up data that's consistent with a story, and you see what proportion of times across repeated samples you get a significant result. And that's your empirical power. So for certain combinations of models and predictors, people have worked out mathematically what it should be, but for anything that's more complicated than that, simulation is the way to do it. And I have lots of examples I'm happy to send anybody if you're in this position. Okay. Other questions about power or anything else? Or snow pants? I also learned that snow pants stopped being a thing past like age 6. Like, I looked for bigger snow pants for my son for this year, and I could barely find any. So I'm like, guess what? You're wearing your snow pants that are like 3 inches too short, but that's what your boots are for. Make it work. I'll deal with this problem next year. I guess if you're going skiing, maybe you get snow pants. Target is the source for snow pants. Okay, I will check into that next year. I suspect I have to decide that like in August. Because if I wait till, December when he actually needs them, then they'll all be gone.
You don't have anything, I guess, Amazon, you can find anything.
Amazon, yeah, I looked, and it was like, all I could find were like the ski kind that were super expensive. Like, no, my kid just needs to play at recess. Like, I'm talking $30 snow pants. So, anywho, I digress. Target online before the snow comes, yeah, or maybe next year, like if they have a clearance. I can try to guess how tall he's going to be next year. Work backwards. That's kind of like a power analysis,
Yeah, it
right?
is.
It's like, how tall is my son going to be next summer, and can I buy this shirt that's on clearance and make it work? I don't know. I'm 80%
Just
certain
buy-
that he can
buy
fit.
big one and let him grow into it.
There you go.
Yeah. His clothes are all too big. That's what it amounts to. It's like, well, he'll get there eventually. Anywho. Where was I? I'm talking about snow pants. I'm off topic. That's what I am. Let me get back on topic. So the last question is what I like to call foreshadowing. Because guess what? Your next homework is available, in which this is section 1. Literally, it's a 4-group problem, and this is me walking you through the logic of what you're going to end up having to do in software. So consider a general linear model with a single categorical predictor that has 4 categories, so 4 groups, and answer the following. So first question, sub-question I should say, what is this called? Anova. A one-way Anova because it's one predictor. Can you guess what it would be called if I had 2 predictors? You would think, but yeah, 2-way. After that, it becomes factorial ANOVA. Like if I had a 2 by 3 by 2 by 2 type of like 4 combination thing. Yes, this is an analysis of variance. So that could be like an EG to describe the model in your results section. Given a single model intercept for a reference category, how do you know which one is to be the reference? Because it says in the instructions. How do you know which is to be the reference in your lives? Whichever you want. There's no wrong choice. You can make any group the reference. I would pick the group that you have the most questions about because all of your model parameters are going to have something to do with the reference group. So it makes sense to put the group that has the most importance to you, or the one that's the most prevalent would be another good way to choose. But there's no wrong choice. It just dictates how the model parameters are interpreted. So given a single model intercept, how many fixed slopes do we need to be able to differentiate the mean for the other 4 categories? So how many slopes do I need if I got 4 categories? Yeah, this is a finger question. 3. Yes, indeed. Because then I have 4 fixed effects and I have 4 categories. And I get it exactly right. Each group gets its own predicted outcome mean, and I can ask the model about any of the group differences that I want. If I were to put in fewer than all possible slopes, then one of the group means is not going to be exactly right. There are situations in which you might want to do that, but not for this homework. So 4 groups requires 3 slopes, which means how many new predictor variables do you need to make? How many new predictors do you need that are going to carry the slopes? I've had people like, I had my fingers up, but now I'm taking them down. The next question is how many pairwise mean differences? Folks are answering that one, 6. 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. Got them all. And there is an equation you can use if you run out of fingers to do the counting. But for 4 categories, I know there's 6. But my previous question was related to this. If you know that you need to put 3 slopes in a model, how many new predictors do you need to make? Not a trick, I swear. 3. 1 for each. So when I say put 3 slopes in a model, what I mean is create 3 new variables, each of which has a 0 or 1 value, and give them slopes in the model. So 3 new variables for 4 groups. 6 possible differences. How many are given directly by the fixed effects? You don't have to ask for any other information. 3. Because it's each group relative to the reference category. That's what your new predictor slopes are going to tell you. That means if there's 6 possible and 3 of them are already in there, how many are left? 3. Now you may not want to know all 3 of the ones that are left, but that's how many are possible. There's more theoretically possible than that because you could lump groups together. So for instance, if I had 1 control group and 3 treatments, I might want to know, is the average of the 3 treatments different than the control? I could ask that question too. And that creates yet another potential hypothesis test of interest. So I had a couple of people say, yeah, I'm not really sure how to figure this out, or I'm not sure what you're asking me. So let me review where I was pulling that from. This is this example right here. This is slide 9 of lecture 3. So I had, as an example of 4 groups, a control and 3 different types of treatments. This is the same type of story that will be in your homework. And given 3 new variables that I create with these blue boxes here. So step 1, make these new columns in your data set where the reference group is given zeros across the 3 new variables, and then each new variable turns on when it's that group's turn. So this column is directly going to tell me how treatment 1 differs from control. This column's slope is directly going to tell me how treatment 2 differs from control. And this one is treatment 3 versus control. So that's what I mean by directly, meaning the fixed slopes that show up in your output directly tell you that set of differences. The ones that are not given, is treatment 1 different than treatment 2? I don't know. But it seems like I could know that, right? Because I've got this one versus that one. And it turns out that that's exactly how you solve the problem. It's the slope for this variable minus the slope for that variable. And if I wanted to know treatment 2 versus treatment 3, it's the slope for this variable versus the slope for that one. So that's what I mean by implied by the model, or require linear combinations, because you have to go between the slopes to get the answer. And the next slide then spells out that logic more specifically. If I want to do, say, treatment 1 versus treatment 2, I know that the model tells me the predicted outcome for treatment 2 as beta 0 plus my new slope for beta 2. I know the model tells me the predicted outcome for treatment 1 as my beta 0 intercept plus my new slope for beta 1. The difference between these, it's beta 2 minus beta 1. And for these two, it's beta 3 minus beta 2. And for 1 and 3, can you guess what that would be? That one versus that one? Beta 3 minus beta 1. Yep. So that's what the estimate statements in SAS, the LinCom statements in Stata, and the GLHT statements in R are doing, is getting those additional differences between the groups. Other instances in which you would want to know linear combinations of fixed effects, anytime you wanted to test the relative importance of 2 variables. So in my other class, I had a homework that you will see a version of. If you want to be more likely to get a job when you graduate, should you have more conference presentations, or should you have more peer-reviewed publications? Like if you only had to get time to get 1 more of each, which do you think is more important? Well, that's an empirical question if you have data to answer it with. So because the units in that case would be like number of posters versus number of papers, you could actually compare those 2 slopes and see if the effect of 1 more is different depending on what it is 1 more of. So there's a lot of different situations in which you want to be able to test differences across slopes in a model. And I want you to be able to do that to answer any question. So I think we answered all of those. Yeah, that was the end. So any questions on this? So I will give you a heads up with respect to your homework. This is a study conducted by the Department of Recreation Sciences at Midwestern State University, examining the robustness of training in mini golf. So people are going to receive training in either mini golf alone, regular golf alone, or a combination of the two, and then compete in a high-stakes mini golf outcome tournament. Now, I'm making a point of saying this for a couple of reasons. One, the story is based on real life, because the first time that I ever met my husband's family, when we went to California to visit them many years ago, we played mini golf. And my normally very chill, very calm husband turned into like a monster with respect to the trash talk with the mini golf and his sisters. It was like a whole thing. I was like, what happened here? Like, I've never seen people take mini golf so seriously. So being in that environment inspired the story. And then I went and played mini golf with my family, and my dad blamed his lack of skill on conflict with his regular golf game, that somehow those were distinct skill sets to be successful in regular golf versus mini golf. So I put those two together, and that's the story for your homework. And also, golf is an outcome in which higher scores are worse. So if a group has a lower score, then their training helped them. So it's different than a lot of outcomes that you may used to thinking about where higher is better, but there are a lot of outcomes in life where higher is worse. Like if we're studying things like unemployment rate, or recidivism, or criminal behavior, or anything where more is worse. Drug addiction, abuse. So think of golf score as one of those where more is worse. And if your score is lower, that is a good thing. So you can start working on that anytime you'd like. It's not due for about 3 weeks, but just in case you feel like doing something that is not something else. Like avoiding some other task by doing homework in this class, right? It's like procrastination, but it's actually productive. Yeah, some of you are nodding. Yeah, I know. It's like, well, I could get started writing this article, or I could do this other task that is much easier to get started on. Yes, that. Anywho. Any questions on this before I shut her down? Okay, I'm going to shut the webpage down. Not the whole thing. It's not that time yet. But we do have this. So we started talking about something a little bit new related to significance testing last time. Do you remember what it is? Our new friend F? F value? Yeah, F test statistic. So what is F for? What is its purpose, broadly construed? Do you remember that part? If the answer is no, then that tells me where we need to start from. The answer is no. Yeah, well, that stands to reason. It's garbage day. That means that it was 5 days ago that we talked about this, right? I don't remember what I was wearing yesterday, let alone what happened 5 days ago. So we can go back to that. So picking up then on slide 11, how about that? Comparing. Maybe. Comparing what? What is F for? The models? Yes, if you think about the models as an empty model versus a model that has more than one slope in it, that would work. Yeah, so we're narrowing down, converging in the chat window here. If the slopes work together, yeah. So F is used to answer questions that involve more than one slope at the same time, broadly construed. Up to this point, we've used T. T is for one slope. So one slope is all we need to know if we have a model that only has one predictor in it. When would we need only one predictor? Well, if we have a linear effect of that predictor, or if the predictor is binary, or we only care about one thing. But most of the time, we care about more than one thing. So to supplement what we can learn from T for each slope individually, we call on our new friend F, which is to lump things together. So F is a more general idea. This is one specific instance of it that we will see. In this context, back to a 3-group example, we want to know whether or not these two slopes work together, beta 1 and beta 2, to answer the question, overall, does group as a predictor matter? Like, is there a significant effective group? And the answer to that question requires 2 slopes in it, not just one. So this is a test then that has 4 pieces going into it, into F. We're talking about information explained, information left over, how many slopes we spent to explain it, and how many slopes are left over as the 4 things that go into this. So number of slopes that we used has a name called numerator degrees of freedom. Number of slopes that we did not spend yet but we could have is denominator degrees of freedom. And those terms go into where they are in the F test. Denominator degrees of freedom is a function of sample size. So it's n minus k. Sample size n minus k is the number of fixed effects you spent, counting the intercept. Numerator is k minus 1, not counting the intercept. Why don't we count the intercept? It's always in the empty model. The question is how many other slopes we need besides it. Then the information part. That comes to us courtesy of something called sums of squares. Sums of squares all have the same concept into it. It's something minus something as a point of reference. So this one is for total sums of squares. It's what you know of as the numerator for the formula for variance. Y sub I minus Y bar. So that is all the offnesses of each person from the mean, and that's going to be the total variance in the model. We're going to carve that up into explained versus unexplained. So then the 2 ratios get built. Model sums of squares. If we look into the formula here, y hat. What's y hat again? Predicted. What the model says y should be. What the model says y should be for each person. That's what the sub I means. Minus the mean. So the mean is what the model predicts in the empty model without any predictors, right? Everybody gets a mean. So this is like, how much better did we do by adding something custom? Not just giving everybody the mean, but basing it based on their group or their whatever. So this is like explained information. So how good would we do? This good. How many slopes did it take us to do this good? So we take sums of squares for the model, information explained, divided by number of slopes. So this becomes like information per slope. Then the bottom part, what's left over? What are all the reasons why we got it wrong? Meaning the y we predicted for each person is not the right answer. So that's the bottom. Y sub I is actual outcome minus y hat that's predicted for you. So this term in parentheses here is another letter. What is it? That idea of how far off the model is, what letter is that? Leftover, yep, that's E. Yes, this is E in here. How far off the model is from the real outcome, the model predicted outcome from the real one. E, residual, leftover, error, trying to think of other words. Residual, did I say that one? It's up here. Yeah. So this is the numerator of variance, because what we're eventually getting to is residual variance. Information left over divided by the number of slopes we could have spent but haven't yet. So then our friend F is built as a ratio of those things. F is mean square model over mean square residual. Information known per slope divided by information unknown per slope we could have added. So did our model do as good as we would expect sort of by random chance of just adding stuff? So F is always positive. If we added something and it helps not very much, it would be 1. So then here's my F distribution. F is always positive. So I keep saying this because some folks get confused and they think, well, if my F is positive, that must mean that my slope is positive, right? No. F is always positive because it's in squared units. F is always positive because we're in squared units, because some of the slopes that F is lumping together could be positive and some could be negative, so we don't want them to cancel, and that's why we have squared units. So to remind us about our decision criteria, if F is greater than its critical value, we say we reject the null, significant. If it's not greater, then we say do not reject the null, non-significant. And this was the table that we ended up with, I think. I think this is about where we left off, slide 18. So this is a summary of what happened with respect to the overall model, lumping my two slopes that distinguish my three groups together. So there's two things in here that are relevant to report. One is the significance test. That's my F right here. So 42 is a test statistic. Cough, cough, homework question. So F is a test statistic, just like T is a test statistic. F is used for more than one slope. F has a p-value that goes with it. In this case, it's going to be a very small p-value. And the last piece of this is an effect size, variance accounted for, which is R square. And the formula for R square, let's back a couple slides, it is sums of squares total minus sums of squares residual over sums of squares total. Meaning, total information minus leftover information divided by total information. So what proportion has been accounted for by the model? That's R square. So in our example, R square is 0.103. So I can interpret that same number two different ways. I can say, think of it as a proportion. So 10% of all the reasons why some people make more money than others is attributed to this predictor variable right here that takes two slopes to talk about it. So 10% explained, 90% unexplained. Question?
Yeah, so how do you know how much percent explained is a good?
Is it good? So this is an effect size. It works the same way as other effect sizes in that we can say whether it's significantly greater than 0, and that will be a function of sample size and effect size. But this is a number that just means what it means. So in your field, 10% may be huge. In someone else's field, 10% may be not good enough. It just is what it is. It's 10% out of possible. So F tells me whether or not R square is different than 0. So these two go together conceptually. In the same way that I have a t-test statistic that talks about whether a slope is different than 0, and I can make an effect size out of the slope that's R or D, I have an f-test statistic that talks about whether R square is different than 0. So R square goes with F, R goes with T. The other way I can talk about this is to unsquare it. So R square is related to R by a square root. For whatever reason, when we talk about R square, it's a capital R. And then when you square root it, it's lowercase r. It just is that way. But R is a correlation. So the other way I can think about this number is if I took my column of y hat predicted outcomes and added it to my data set, and I got my column of actual y outcomes, and I asked for the correlation between these two, the square of that correlation would be 0.103. So that's where I had, on this slide that we went over a little bit ago, slide 22, R square of 0.103, the square root of that is 0.32. So the y hat that's predicted from categorical income level is correlated 0.32 with actual income. And is that R significant? Yes, it is, because f is significant. So this f is the significance test of this r-square. Is the outcome that's predicted by my model correlated with the actual outcome? Yes, f says so. F is significant. How correlated is it? Square root of r-square. Okay, how are we doing? That's fair. I've got a few thumbs and some head shakes. Maybe we would thumb sideways voting system again. Yeah. Fair enough. So broader concept is level of specificity about what happened here. We started in on very specific, like what happened with this slope? And now we're trying to broaden it to how do the slopes work together to make a prediction, and how good is that prediction? We're trying to answer the latter set of questions. How good is that prediction? And is that prediction significant? That's created by the multiple slopes. So this is the type of table that you will see in your output if you use SAS or Stata, and it's spread across places if you use R, unfortunately. So in example 3, for instance, we worked through the individual slope results for this. This is the table that SAS gave me. This is page 4. So that table and this. And I've put in bold the things that would show up as answers in your homework, because these are the things that show up in results sections describing your model. So degrees of freedom, that's what this column is for. When you think degrees of freedom, think number of slopes. Slopes come in 2 kinds. What did I add? What could I have added? I got 2. I could have had 731 more, because I have 733 people. Or 733 plus 1, because I don't count the intercept. So you'll be asked to report those 2 numbers. The reason you need those 2 numbers is because those 2 numbers clarify what the reference distribution is for f. F is, go back to find a picture of f. Yeah. So f has a different shape based on degrees of freedom. It's easier to hit the 5% unexpected mark the more people you have, which translates into more denominator degrees of freedom. So like these 2 curves right here are both models that have 8 slopes. Where 0.5 starts is different because the second one has 40 denominator degrees of freedom and this one only has 4. So there's more area in the tail if you have fewer people, the same as with T. So the standard for what a good enough F is based on these 2 denominator degrees of freedom. Next column over, don't need to report it, don't need to report it. But those are called sums of squares. The first part, information captured. The second, information left over. So the rows here, model is synonymous with explained, accounted for, predicted, captured. All of those words mean model. That which we know. This one, that which we don't know. Error, residual, leftover, unexplained, unaccounted for, remaining, all those words go together. If I take information that we know divided by the number of slopes it took to know it, that's mean square. Information that we don't know, sums of squares error, divided by number of slopes we still could have added, that gives us mean square error or mean square residual, which has a special name. What's this called? Feel free to read from the screen. I'm shameless in encouraging participation.
The mean square.
Yeah. Residual variance, yes, otherwise known as the first question on your homework for every single model. The reason is because if you get this right, you have the right model. You have the right outcome variable, you got the right predictors in it. So do not pass go, do not collect $200 unless you have the right residual variance. Last but not least, this one, mean square model, information captured per slope divided by information remaining per slope remaining, that's our friend F. And probability greater than F is what? That's SAS for what? It's a letter you've already met. P-value, yeah. This is the p-value that goes with the F. So this number is compared to alpha. P less than 0.05, F is significant. P greater than or equal to 0.05, F is not significant. So less than 0.01% of the time, we'd find an F of 42 if the two slopes we put in our model were truly zero in the population. Question, and alpha will be connected to the individual slopes or the model as a whole? Oh, what a great question. That depends on who you talk to. In the strictest sense, everything should be less than 0.05. So if you're going to have multiple p-values, you should take them and discount them for how many you have. That's what's known as family-wise error rate. What I think is more common is to look at each p-value and talk about it as if it's relative to 0.05. But keep in mind that for every 20 p-values you look at, one of them is going to be significant by chance. There are, in your textbook, there's a lot of discussion on correcting for alpha inflation by doing multiple tests, and there's various procedures that are proposed to deal with this issue. In my world, for simplicity, we're going to say 0.05 for everything. But that's admittedly a somewhat lenient standard, rather than saying 0.05 across the board. So this F of 42 is significant, yay us. How good is our model? It's significant. How good is it? It's significant. Well, what goes into significance? Sample size and effect size. So is this F significant because I have 734 people? Or is this F significant because I have a strong model? Can you think of a way I can resolve this conundrum?
I was thinking about that for a long time.
Effect size, right? I need to pull the effect size part back out. That's what our friend R square is for over here. R square is an effect size for how good our model is. How good is your model? It's significant. How good is your model? I got 10% of the variance. Oh, okay. And that 10% is significantly different than 0. Is 10% good enough? I don't know. That's a philosophical question, and this is not philosophy class. I had to pass no pass philosophy class in college so that I wouldn't tank my GPA because I couldn't handle philosophy class. I could not. I read the Cliff Notes. I read the books. I was like, what the hell is Plato talking about? I cannot with this. So I am the wrong person to talk to about philosophy. But I can tell you, I got a significant model. How good is it? It's 10% good. Whether that's enough is a different question. So why are only some of these numbers bolded? Because only some of these numbers are reported. Why are some of these numbers reported? Because they're the ones that it takes to recreate everything else. So if we work backwards, I have to report F, and I have to report degrees of freedom. And I also have to report mean square error, which is my residual variance. So if I have these two numbers, I can get this one. Because f times residual variance is going to give me back mean square model. And if I have the mean squares and I've got the degrees of freedom, then I can multiply the mean squares by the degrees of freedom and get back to sums of squares. And if I got sums of squares, then I got r square. So this whole set of results would basically be summarized by this one sentence right here. And this is the type of sentence that you will get practice filling in your homework. F, then in parentheses, numerator degrees of freedom, denominator degrees of freedom, equals the F value, followed by the mean square error for the amount of residual variance, followed by the P value for the F, and then if it wasn't already given someplace else, the R square shows up in here too. So in my write-up for this, for example, this is what it would look like. Here's a full sentence. We found that class membership significantly predicted annual income, comma, stat, 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 and then words. Relative to lower classes, the reference group, we found significant differences for middle class and for upper class, but not middle and upper were not different from each other. So it's like a funnel. We start with, what did we do? What did we find? Big picture. My model. Is it a good model? It's significant. How good is it? 10% good. Proceed. In my 10% good model, this is what happened. More specifically, these are the slopes that I found, these are their differences, these are their significances, and these are their effect sizes, which I did D in this case. And in your homework, all of the numbers that show up in the results section are populated from your answers. So you can always look at the number, go back to which question it was from, and know what the number is referring to. But that doesn't mean the numbers are right. So I've had people be like, but it's right down here. How come it's not right up above? No, it's what you set up above, and it's pulling the value you entered and putting it down below. So the numbers are internally consistent, but you will only know if the values are correct if they turn green. Once they turn green, you know they're correct, and you can find them down below and know what they refer to. So this is what it looks like for this type of model in SAS. And I wanted to show you what it looks like in the other programs as well. So I have opened up the output file that goes with the example 3 download packet. This is what it looks like in Stata. So the second table is placed sort of off to the side, but otherwise it's organized the same way. Stata labels model and residual rather than model and error. This is the sums of squares column. Degrees of freedom column is to the right instead of the left. This is the mean square column. Here's my magic residual variance, mean square residual. F is over here, and it helps you out. It gives you the degrees of freedom right next to the F. Here's my R square. Adjusted R square we haven't talked about yet, but that is an adjustment for small sample sizes. And if you want to have the average, basically if you take the residual variance and take the square root of it, it's that thing right there. It tells you that as well. So those of you who are using SAS and Stata, this information is presented in this fairly regularized format, not so much with R. So here's the R output for the same model. The first thing that I asked for out of the R output is the Anova option, because it gives you sums of squares for each of the slopes, and it gives you the mean square residual. So this table is not sufficient to answer everything, but you can get part of it. So the reason I asked for this table is to get this number right here, residual variance. It's not given elsewhere. Then the summary function that comes out of the model gives you the individual coefficients, the slopes, intercepts, their estimates and standard errors and significance tests, and then you get this little chunk of text right here that replaces the table. Residual standard error. That is residual variance's square root on 731 degrees of freedom. Is that numerator or denominator? Make it a little bigger. Because it just says degrees of freedom. Which one is it? That's denominator, yeah. Number of slopes left over. Then it gives you multiple r squared. And then it gives you the F statistic and the p-value. So it looks closer to the way that you would report it than the way that the other programs organize the information. For better or worse. But it's all the same information that's being presented. So I have, in my code, asked for these pieces of output in the same order in which they would show up in the other packages to try and keep it consistent. So just to recall, the Anova function, the only thing you need out of that is this number right here, which is your mean square error. Otherwise, all the stuff that's related to your F-test for the model shows up in words underneath your output. By the way, this p-value, at the top of my code, there is an option to turn off scientific notation. It's not in this output, but that's why if you get scientific notation in here, you can change it. There is an option called SCIPEN, and I don't know what that stands for. But I asked the internet, how do I turn off scientific notation in R? And it told me. So, all right. How are we doing? A lot, huh? I know. The good news is that honestly, there's not that many new concepts left this semester. It's like the new part is pretty much done. It's just like extensions. F is for testing more than one thing at a time. When would you do that? When you want to know about your model. When else would you do that? When you want to know about a predictor that takes more than one slope to tell its effect. That's your take home. And yeah, and reminding you, why are we just now talking about F for the first time on slide 17? Because we didn't need it before. So in your previous homework in Unit 2, we had only one slope. If you have only one slope, the t that goes with that slope, if you square it, that's your F for the model. And if you have only one slope, the R effect size for that one slope, if you square it, that's your R squared for the model. So now we need F and R squared because just looking at the individual slopes is not sufficient to describe how good the model is as a whole. All right. Adjusted R squared. This is something that reviewer 3 may ask for. Some people really care about this and some people don't. In case you find somebody who really cares about it, here's the difference. You take your regular R squared and correct it for sample size. So this is thought to be a more generalizable version of R squared. In my homework, I'll ask for the regular R squared, but I wanted you to know where the adjusted version came from. So in our example, unadjusted R squared is 0.103. The adjusted R squared would be 0.101. So these values are pretty much the same because we have 734 people. So just as an aside. All right. 307. Hanging in strong on garbage day. That means Tuesday, by the way. Questions or things that you want to hear again or differently? Hit me.
Can you repeat the difference between adjust R square and unadjusted R square?
So this is regular flavor R squared right here, which is a function of sums of squares. And adjusted R squared takes that regular R squared and changes it as a function of n and degrees of freedom.
So what does it mean in the research?
It is trying to correct for a positive bias that occurs in small samples. So it's easier to find a bigger R-square if you have fewer people.
So that means if I have small sample, I can use the adjust R scale in my research.
Yes. Yep. I think as long as you're clear about which one you're using, then someone can tell you to use the other one instead if they have a strong preference. But I think to be on this, the safest side would be to use adjusted R-square because it would be the most conservative. In my homework, I asked for regular R-square because I want to make sure it's consistent across packages, and I know that that one is that. One caveat, regular R-square cannot go negative, but adjusted R-square can. So that's one potential reason maybe not to use it. Okay, let me go back to something real quick. That reminds me of something else I had wanted to say. Let me go back this table again. So there will be questions on your homework trying to illustrate what goes up and what goes down across models with respect to R-square and residual variance because they work in opposite directions. So for these data, back up quite a bit here until I get to the empty model. For these data, there we go. This is the slide I want. Right here. Two models on this page. This is slide 7. Empty model versus my current model. Empty model has intercept only. It's my worst case scenario jumping off point. What should everybody get for their predicted outcome? I don't know, just give them the mean, call it good. And so E is the difference between each person's score and the mean, meaning that the variance of these E residuals across people is just the variance of this variable. So like 190 is the residual variance from this model if I have no predictors. That's how much variance there is to be explained. After I put in my predictors, the variance of the E's, because E is now not just how far off each is from the mean, it's how far off is from the mean that's given to you by these variables as predictors. The E variance is down to 171. So what should happen if your model is good is that the residual variance, the mean square error number should go down because the E variance should be smaller. E captures unexplained deviation. And if you're heading in the right direction, there should be fewer unexplained deviations. So E variance goes down. If E variance goes down, another way of saying that same idea is that R square goes up. R square for an empty model is what? Let's back up. What's R square conceptually?
It's R squared, correlation squared.
It's correlation squared, that's one. What is it as a proportion? Like I said, my R square was 10%. What's that mean?
10% explained.
10% explained. So if I have an empty model with nothing explaining in it, what's R square? 0. So in other words, the 190 is all the variance. We have explained none of it. If the variance drops to 171, we have explained some of it. More specifically, we have explained 10% of it. So residual variance goes down means R square goes up. And the best possible R square would be a 1, right? You got all the variance, which would mean that this residual variance number is down to what? 0. Yeah, perfect. No E at all. I'm able to predict with 100% accuracy what each person's outcome is by my model. That would be R square of 100%. Residual variance is 0. So I'll say that again. As residual variance goes down, That means R square is going up. R square is capturing the proportion by which the variance went down. There we go. Now I got all those words in the sentence. R square is capturing the proportion of variance that went down. Explained. Because what we get is what's left. Okay, other questions before we call it a day? Any that you need to hear again?
One quick clarification, please.
Yeah, hit me.
When you say that the R2 captures a proportion from which the variance effect, or the variance went down, that's from the empty model to the
Yep,
corrected model?
that's
Okay.
correct. Yep. Yep, and I'm making a point of saying that it's relative to empty because where we're heading is having more than two possibilities. Like, what if I put group in my model, and now I want to control for age 2, right? Then hopefully, if my predictors are helping, my residual variance will continue to go down, which means my R square will continue to go up. And so that'll be one of the things we look for in judging, okay, how much better did my model get after adding more stuff to it? Did it get significantly better? Yes. By how much? I got another 5%. Yay me. Yeah.
Because hopefully you're using variables that like are accounting for those differences.
You're using
Okay.
variables that are counting, meaning that they're predicting the outcome.
Yep. Okay.
Yep. And even if they don't, that might be noteworthy.
Right.
Like, I thought this should matter, but it turned out not to. Huh. That's still a story. So yes, which is why you should be able to graduate even if you don't have significant results. Because that's not a criteria. Answering the question is the important part. So, anywho, 315. Stay tuned for the exciting conclusion of F statistics. Said no one ever, except me. All right, office hours start at 3:30 once I get back upstairs. Let me know if you need anything. Otherwise, see you Thursday. Thanks for coming.
Yep.